As part of the work of the Neocognition Laboratory, we'll share insights on a burgeoning new field, the neuropsychology of AI. Indeed, this video will introduce you to this discipline. Our discussion will be based on the article, Psychology of Artificial Intelligence, Epistemological Markers of the Cognitive Analysis of Neural Networks. What is the nature of the cognitive processes and contents of an artificial neural network? In other words, how does artificial intelligence fundamentally think at the neuronal level? And in what form do its knowledge and cognitive processes reside? The neuropsychology of artificial intelligence aims to study this question. Each formal neuron in an artificial intelligence system is an elementary cognitive building block of this AI system. Each neuron can be analyzed as a dimension of a characteristic, a category of thought considered by this neural system when analyzing texts, or more broadly, the data it processes. These dimensional characteristics can be linguistic, for example, phonemic, phonetic, morphological, syntactic, lexical, semantic, or pragmatic. Visual, such as hue, saturation, brightness, contrast, depth, shape, or resolution. Auditory, like frequency, intensity, duration, timbre, pitch, melody, and rhythm. But also logical, contextual, qualitative, quantitative, and others. A neuron can, for instance, specialize in detecting a specific shape, circular, triangular, rectangular, or a specific color, green, blue, red, or even bright, dark, flashy. It can also detect relative positions in an image, in front of, above, behind, or concepts within a text, related to family, illness, love, or cold. However, these characteristics can also take on entirely other imaginable forms, whether these pertain to categories of thought and terms humans possess, or to alien concepts reflecting categories of thought humans do not currently use or recognize. For instance, an alien concept could pertain to a uniquely intricate blend of subtle facial microexpressions and nuanced shifts in body postures, imperceptible to humans, that communicate complex intentions in social interactions. Another might involve a temporal, climatic, and geological cycle in which unidentified oceanic microphenomena predict climatic events on an unconventional timescale not yet considered by current human models. Another could identify pathological olfactory signatures, enabling instantaneous diagnosis of somatic diseases based on scent. Research in this area is already advanced. A neuron in layer n+1 is generally connected to all neurons in the preceding layer n. In other words, the category of thought represented by a neuron in layer n+1 is constructed by combining, in certain proportions, the categories of thought carried by the neurons in the previous layer n. This cognitive activity of creating new, original categories of thought is driven by the mathematical function specifically defining each neuron, its aggregation function. This aggregation function resembles a recipe. It specifies the particular ingredients, initial categories of thought to use, the proportions to apply, weights of the aggregation function, and how to combine them, the summation operation. It produces a specific output, a new category of thought resulting from mathematical operations of selection, weighting, and additive coordination. For example, a new color category could be created by mixing 40% blue, 30% yellow, and 30% green. Or a new economic categorical abstraction called eco-resilience might be developed to evaluate companies' robustness and sustainability in the context of climatic and economic uncertainty by combining, using selected weights, various preliminary categories, environmental, social, and governance indices, along with resilience ratings for climate crises such as past economic stability and supply chain diversity. In Gérard Vergnaud's terms, synthetic categories of thought are knowledge in action. They are not conscious, verbalized, justified, or demonstrated. Rather, they are empirically constructed through experience during the training phase of the neural network. These categories are deemed effective based on their utility for the tasks at hand, as indicated by feedback provided to the network during training. More specifically, the artificial categories of thought constructed by an AI system are concepts in action. In terms of formal logic, these are arguments, objects of thought, and predicates, properties, relationships, transformations that can be applied to those arguments. Examples of arguments include user's face image, child, size. Examples of predicates are similarity of the user's preferences with those of others, contextual relevance of provided responses, is taller than, is round, or how optimal the trajectory is for obstacle avoidance. These synthetic concepts in action are developed because they have been empirically proven relevant for effectively managing the data processing tasks required of the neural network. The aggregation function of a neuron constitutes a theorem in action. This synthetic theorem in action, specific to each neuron, acts as the code or formula detailing which concepts in action, from preceding neurons to prioritize, how strongly to account for them, and how to combine them to produce the new concept in action, that is, the thought category, unique to that neuron. This newly crafted concept in action is a category of thought that is finer, more abstract, and more functional for accurately analyzing the data presented to the network and classifying them effectively according to the task's objective. Successive neural layers thus serve to create operational modes, that is, synthetic theorems in action, for constructing increasingly adapted and efficient new concepts in action, aligned with the expected actions of the AI system. The purpose of neural networks is therefore pragmatic, not epistemic. It is not about understanding, but acting effectively. This involves constructing synthetic knowledge in action that proves to yield results deemed satisfactory. The categories of thought constructed in action by a neural network do not arise from decoding the natural characteristics of a pre-existing world. These concepts are actively generated and do not reveal a world that was already there, as an empiricist epistemology might suggest. From an embodied cognition perspective, the thought categories generated by a neural network directly depend on its particular architecture, specific mathematical configurations, and the data used during its training. Thus, synthetic concepts do not describe the world as it is, but rather the interaction of the AI system with its inherent properties with the world. In other words, the categorical dimensions are not an analog copy of a pre-existing external world, but a constructed representation of the internal experience an AI system has of the world, shaped by the specific modalities of its neural network organization. The strength of a neural network does not lie in faithfully reproducing so-called true properties of world objects, but rather in segmenting the world by making functional regularities emerge when the network, with its unique cognitive and mathematical capacities, interacts with the external world. Thus, formal neurons do not decipher the properties of the world, they make them emerge by acting cognitively upon it. The neuropsychology of artificial intelligence seeks to uncover, at the neuronal level, the specific cognitive and mathematical characteristics, explaining the initial genesis, evolution, and functionality of synthetic categories of thought unique to neural networks. Thank you for joining us on this exploration of synthetic thought in artificial intelligence. You can find the article mentioned in the video, as well as all the work from Neocognition Lab on neocognition.org. See you soon for a new video.